Okay, so the book has sort of a cool example here, um, to start you off. Suppose that a car dealer offers to sell you a car for $18,000 or for payments of $375 per month for 5 years. So this is sort of an introduction into section 4.7 Newton's method. Okay, so all right, this is not, this actually is not uncommon. People making car payments for their car. You would like to know what monthly interest rate the dealer is in effect charging you. Okay, and to do that, you have to solve this equation here. Okay, 48x times 1 plus x to the 60th power minus 1 plus x to the 60th power plus 1 equals 0. Okay, so does that look like an easy equation to solve there? Does that look like something you could? Does that look like? Definitely not. Uh, you learned in pre-calculus. How many remember using things called like the rational root theorem for finding, for finding candidates for rational roots, and then you use synthetic division to find the root, and then you break the polynomial down, break the equation down, and then you find some other roots. How many recall doing that in pre-calculus? Okay, Ian doesn't recall it. Well, I taught pre-calculus. I taught that. It's part of it. So it's Nicholas recalls a little bit. And of course, for this kind of problem, we wouldn't be doing this analytically. We would not be finding the root, analytically. And the root, the solution, well, the value of x is not something that is easily found here. Okay, and they talk about in the book that, quadratic equation. Of course, if you have a quadratic equation, that's easy enough to solve for x. For third and fourth degree equations, there are formulas for the roots, but they are complicated. There are actually formulas to find the roots for a third or fourth degree equation, but they are complicated. Believe me, they are. And then for polynomial of degree 5, there's no such formula. And then you could have an equation like the cosine of x equals x. There's no formula to find the exact roots for that equation. So what we're going to do is we're going to find approximate roots, approximate solutions. So like this first equation here, equation 1, what they do is they plot the equation. Okay, and you've done this, actually, certainly have done this in your life, because you have these TI 8384 graphing calculators. You know that you can plot of the function corresponding to the equation. If you could plot the function 48x times 1 plus x to the 60th power minus 1 plus x to the 60th power plus 1, and then you could find out where the solution is equal to 0 by using your calculator. How many remember using the 0 function? If you go into your calculator, well, actually, it's in the TI-8384. If you go to, let me see here, where is that 0 function? It's under, yeah, it's under second calc. If you look above the trace key, second calc, hit that, and then there's a 0 function that helps you find the zeros. How many? Okay, so how many? Ian remembers using that. Zoe remembers using that, and Joe, and you've all likely seen that. And that's nice, that's nice. But you might wonder, how does the calculator do that? I mean, at this level, I mean, you've been using that program in your calculator. to find the zeros of a function. And of course, that's fine. You usually get decimals, but you might wonder, well, how's the calculator do that? Okay, so they mention here, how do numerical root finders work? Numerical root finder, for example, is, as we talked about, the zero feature on your TI-8384 calculator. Well, there's a method called Newton's method, and let's talk about that a little bit. Okay, so the geometry behind Newton's method is shown in Figure 2. So here's Figure 2. You have this function f of x. Okay, in Figure 2, you have this function f of x. All right, and I want to make sure I'm going at a good speed here. And you want to find the root of you want to find where the zero of the function. Okay, you want to find the zero of the function, and or the root of the function. Okay, and you know, one way you could do this, I mean, let's just say you didn't, well, let's say that you were just trying to figure out how to find the root. And you know, you're trying to find a way to find the root r, and you don't have your TI-8384 calculator with you. Okay, you don't have it. Like Newton, right? Isaac Newton did not have a TI-8384 calculator. So he had to come up with a way to find roots of functions. So what he did was he picked a point on the function x1 f of x1. Probably x1 would be a nice value, and the f of x1 would be something that's a value easy to calculate. And a tangent line is drawn from the point x1 f of x1, okay, to the curve. So a tangent line at the point x1 f of x1 is drawn. Tangent line to the curve at at the coordinate x1 f of x1 is drawn. And you see how that pink tangent line, it goes down and it intersects the x-axis at x equals 2. Okay, so starting at x1, your initial value, you draw the tangent line to the curve at x with that value x1, and then the tangent line intercepts the x-axis at x2. Is x2 closer to the root r? Is x2 closer to the root r? I mean, x2 isn't hard to find. It's just an x-intercept. That's not hard to find. You can find that without a calculator. Yeah, x2 is closer. x2 is closer. That's right, Ian. It is closer. So, you know, we did one iteration here of this procedure, and we came up with a value x2 that is approximating the root r. And x2 is not hard to find because it's the x-intercept. You found x-intercepts of you know, how do you find the x-intercept? You take the equation of the tangent line, set y equals 0, and solve for x. So you can find x2. That's not a problem. Okay, well, what if we were to continue doing this process? Okay, and that's what they're showing. Well, you know, they're showing here to find a formula for x2 in terms of x1. I guess it's, let's look at this. So, you know, what would x2 equal? What would x2 equal? Well, here is the equation of your tangent line right here. Y minus f of x1 equals f prime of x1 times x minus x1. Okay. And the x-intercept of the tangent line is going to be x2. So to find it, you set y equals 0, just like this. And then you solve for x2. So when y is 0, x is x2. Okay, that's how they get the x2 in there in this equation. Okay, so let me just, hold on. So what I'm trying to say is, well, they won't let me just do highlight, but hold on. Maybe, all right, so how do they get the x2 here? How do they get the x2 there? They let y equal 0. When y equals 0, then that is going to when y equals 0, the value of x would correspond to the x-intercept for that tangent line. So they do that, and then they solve the equation for x2. Okay, they solve it for x2, and I don't know why I can't, let me see, can I highlight it? Yeah, I can highlight it. So just want to make sure I'm trying to highlight, things carefully. But what they do is they solve for x2, and x2 then is going to equal x1 minus f of x1 divided by f prime of x1. Okay, that's your approximation to the root r. x1 was your first approximation. You had to pick a point, on the x-axis close to the root r, and then using the tangent line to the point on the curve, x1 f of x1, you're able to get an x2 estimate to the root. And x2 is better than x1. Okay, so you use x2 as a second approximation to the root r. Are there any questions so far? I want to make sure you're comfortable before I move forward. Are there any questions? All right. Well, so looking at this in the figure here, this x2, whatever that value is, do you think it's a good approximation to the root r? You think x2 is a good approximation to the root r? I mean x2 is better than x1 because x2 is closer to r, but that's right. I agree with you. Not yet. x2 is an approximation to the root r, but it's not a good approximation. Well, what if we were to do repeat the same process and find the point on the curve who has coordinate x2, draw another tangent line down? Would that give us something? Would that give us a value x3 that's closer to the root r? And the answer is yes. You see, that's what they do in figure 3. And x3 is a better approximation to the root r. Okay. And incidentally, the x3, we would estimate x3 then by taking x2 minus the quotient of f of x2 and the derivative of x2. We keep repeating these approximations, and when we do that, that's going to give us the Newton's method that says the n plus first estimate of x equals the nth estimate of x minus f of x minus the quotient f of xn divided by f prime of xn. And all you're doing is you're successively doing these iterations, and each iteration, x3 is a better iteration than x2. And if you were to do another iteration, another tangent line where x3 is, the x3, that x value, well, the coordinate on the function, the tangent line to that coordinate gives you x4, and you keep doing it, and you're going to get a better and better approximation. And this is perhaps how your TI-83, 84 calculator locates roots or zeros of functions. Maybe perhaps this algorithm is programmed in. Okay, there's a whole, this constitutes what's called numerical analysis. And there's a whole course on that. I actually took 2 courses on that when I was in graduate school. And, you know, but how many think, hey, this is kind of cool? Okay, maybe. Joe says maybe. Nicholas says, sure. Okay, all right. So it's clear that if we keep doing this process, okay, keep doing this iterative process, as n gets large, these approximations x sub n are going to get closer and closer to the root. Okay, and that's what Newton's method is. But there is a caution here. There is a caution that the book mentions. So in figure 3 up here, figure 3, Newton's method worked beautifully. But in certain circumstances, Newton's method may not work depending on what your starting value is. And they're showing this in figure 4. Okay, so in figure 4, they say you can see that x2 is a worse approximation than x1. So they draw a tangent line to the curve corresponding to x equals x1. That's your starting value. Tangent line hits the x-axis at x2 in figure 4. And then when x equals x2, they draw another tangent line to the curve when x equals x2. And that gets you to x3. But x3 is further away from the root r than x2 was. Okay, so this is an example where Newton's method is not working. This is an example where Newton's method is not working. And this is why, you know, how many of you have had, well, yeah. So, you know, in this case, Newton's method fails, and a better initial approximation should be chosen. Okay, so for instance, in this, what kind of caused the problem here? Well, it has to do with that tangent line when x equals x2. The tangent line takes you to the x-intercept for that tangent line is x3, which is further away. So if if x1 were positioned a little closer to the root r, you might avoid that issue. But it's something that can come up, and that's, you know, hey, you know, welcome to real life, right? So what I'd like to do is do a problem with you. Are there any questions? Are there any questions at all? Well, actually, let's look at one from the book here. Let's look at one from the book. Okay. Let me see. There was a chat. Okay, hold on. A good question in the chat line here. Yeah, Ian, how do you know when it may be worse? Well, certainly if you have a graph of the function and you know where the root you're looking for is, and you end up getting successive values that like x2, x3, x4, well, maybe x2 is okay, but if you start getting a succession of values, you know, like x3, x4, x5 that are moving further and further away from the root r, then you know Newton's method is not going to converge to the root r. So that's one way. You can graphically see it. You know, your values, if you're converging towards that root, your values, x3, x4, x5, x6, and so forth, have to start getting closer and closer to each other. There has to be agreement in the decimal places in your approximations. So that's how you'll know. And you know, you can't. It isn't always. Well, I want to say this the right way. It's nice to know if your method's working without having to draw the curve, you know. And one way to know that the method's working, usually a way to know, is if your successive approximations are getting closer and closer together, like they're converging to a number. That's one way to know. Very good question. Very good question. All right, Ian. All right. All right. Very good. Very good. So in example 1, what they do in this example is they say starting with x1 equals 2, okay, starting with x1 equals 2, find the third approximation, x sub 3, to the root of the equation x cubed minus 2x minus 5. Okay, so again, you know, well, yeah. So let's just use Newton's method. So first of all, we identify our function, f of x, as x cubed minus 2x minus 5, and then the derivative is 3x squared minus 2. So now we're going to use the Newton's method, okay, and it says here Newton himself actually used this equation to illustrate his method. And he chose x1 equals 2 after some experimentation. Now, I can show you why he chose x1 equals 2. I mean, it's pretty clear here. So what happened was the function crosses the x-axis. Okay, where the function crosses the x-axis is a root. And because f of 1 equals negative 6, okay, hold on here. Let me just, one moment. Yeah, f of 1 equals negative 6, f of 2 equals negative 1, and then f of 3 equals 16. Okay, so f of 1 equals negative 6. That means at x equals negative 1, the function is below the x-axis. F of 2 equals negative 1, so that means when x equals 2, this function is still below the x-axis. But when x equals 3, f of 3 equals 16. That means the function is now above the x-axis. So somewhere between x equals 2 and x equals 3, the function crosses the x-axis. So that's why he's letting x1 equals 2, because he knew that that's a pretty good starting point. Okay, again, you want to pick a good starting point so that Newton's method will succeed and not fail. All right, are there any questions on that? Any questions? All right, well, so what comes next is using the Newton's method. And using Newton's method, of course, the formula is right up here. X sub n plus 1 equals x sub n minus the quotient of f of x sub n over the derivative f prime x sub n. And so now for this example, it's really a lovely example. X sub n plus 1. Let me see here. I just want to highlight it. One moment. But I don't think I want it in blue. Hold on, class. All right, x sub, well, all right, let me just see what's showing up here. Yeah, this is fine. This is fine. X sub n plus 1 then would equal x sub n minus the quotient of x sub n cubed minus 2x sub n minus 5 divided by its derivative, 3x sub n squared minus 2. Okay? And so first approximation we get is x sub 2. So x sub 2, all right, would have to equal x sub 1 minus the function minus the quotient of the function f of x sub 1 divided by the derivative f prime of x1. And x1 is equal to 2, so you just plug in 2 everywhere. Well, basically now you have, they have the formula. You just plug in 2 everywhere you see the x1 and you get 2.1. All right. Are there any questions on that part? Any questions on that particular part? It's just computation. All right. Well, now we want to do another approximation, x sub 3. Well, x sub 3 is going to be based on x sub 2. And so x sub 3 is going to be equal to what you see here. I don't think I need to read every little detail. You can see it right in front of you. I mean, this is how, a lot of math, well, all of math really, it comes from a need to having to do things. Newton needed to find roots of functions, and he came up with this method. Okay, and we use this method today. It's just the method is programmed in calculators and computers, but the method is used. Okay, and you should know how this method works. Okay, are there any questions on this? Turns out this third approximation, okay, x sub 3 equals 2.0946 is accurate to 4 decimal places. And they have a little figure down here showing the geometry. And you've seen that from before. Based on the previous figures we looked at, how Newton's method works in terms of the geometry. Are there any questions? All right, let's go down a little bit. This gets to they talk a little bit about knowing when to stop, and this is we can keep doing Newton's method, keep going and going and going for the iterations, but how do you know when to stop? Suppose that we want to achieve a given accuracy in 8 decimal places using Newton's method. How do we know when to stop? The rule of thumb that's generally used is that we can stop when successive approximations agree to 8 decimal places. Okay, 8 decimal places. Okay, so, that's just a choice, but sure. All right, so are there any questions? Any questions so far with this first example? 8 decimal places might be good, but if you're doing an astronomy computation, you might want more. You might want more accuracy. So it really depends on the application. All right, well, if there are no questions, then let me go ahead and bring my example. Now, my example is really example 2 from the textbook, but I'd like to just sort of take you through it here. So let me bring the example up. Okay, let me give you a moment to copy this example down. Okay. Okay, so in this problem, we want to use Newton's method to find the sixth root of 2 correct to 8 decimal places. So we have to think of a starting value of x. Okay. We have to think of a starting value of x. And by the way, does anybody offhand know the sixth root of 2? I don't think so. I don't think so. So, all right. Well, I'll tell you what. First, we know that with Newton's method, we need to have a function, right? What function do you think would be a function if I want to compute the sixth root of 2? What function would have that root? Something minus something. What function would have the root, sixth root of 2? I'll give you a hint. There's going to be a 2 here. And now what's going to go here? In that spot. Well, the thing, I'd like a polynomial. I'd like a polynomial. Okay, I'm not saying this isn't the only function, but could I have x to some power here? Well, it wouldn't. 1/6. You're almost right, Joe. What power has to go here? Joe's so close. Now, there we go. That's right, Joe. X to the sixth power minus 2. Because if you take x to the sixth power minus 2 and set that equal to 0, you're going to get x to the sixth power equals 2, right? And if you then take the sixth root of both sides. Okay, I know this is good. I just need I need the space. If you take the sixth root of both sides, you're going to get x equals the sixth root of 2. So for the function f of x equals x to the sixth minus 2, that function, where it crosses the x-axis, would correspond, that x-intercept, the root of that function would be x equals the sixth root of 2. Okay. Are there any questions on that? All right. All right. Well, let's go to the next. Let's go to the next page here. So, finding the sixth root of 2 is equivalent to finding the positive root of this equation, and therefore we're going to let f of x equal x to the 6 minus 2. And I just verified, you know, that for you. So sometimes you have to come up with the functions. Okay, sometimes you do. Let me see, there's a question here. Why not negative? Let me see. Trevor, could you be a little more, I'm not quite sure, when you say why not negative, what do you mean by negative? Do you have another function in mind? Oh, okay. Well, the reason, okay, I see what you're saying. I understand now. Well, let me ask you this. The sixth root of 2, is that a positive or a negative number? The sixth root of 2. It's a positive, and that's why they want you to focus on finding the positive root of x to the 6 minus 2. Okay, very, very good question. If you, let me just see, I'm actually, x to the 6 minus 2, this function here is an even function. It's symmetric about the y-axis because, you know, you have even powers only on the right side here. And there are 2 roots for this function, x to the 6 minus 2. If you were to graph it, maybe I can do a quick graph here. If you were to graph okay, if you were to graph x to the 6 minus 2, your graph would look like this. It's symmetric, so it's like, hold on, I want to draw it so it's symmetric. The left side looks like the right side. Okay, so let me try to be a little bit neater here. Yeah, that's better. Erase this here. This here is f of x equals x to the 6th minus 2. And there are two roots. So there's of course, this is the origin here. There are 2 roots. And the root that we're interested in is this root here, the positive root. That's what they mean, Trevor. Very good question. So we have to choose an initial approximation. And I'm going to choose x1 equals 1. Why? Well, first of all, the 6th root of 1 equals 1, which is an easy starting point. It's sort of a natural starting point. It wouldn't matter. Well, I got to be a little bit careful here. In this problem, it isn't going to matter actually what your starting point is, but look at the first computation, okay, when I use the Newton's method. here, and of course f prime of x equals 6x to the fifth. When I use Newton's method with x1 equals 1 to approximate x2, it's very easy to compute my function, okay, f of 1, and my derivative f prime of 1. It's very easy to compute those. So that's you know, if anything, it's a nice reason to start off with x1 equals 1. Okay. So Joe, I just chose x of 1 equals 1. I chose it. I say let's choose, but you don't have to choose x of 1 equals 1. You could have chosen x of 1 equals 3. Okay, you could have. But usually you choose, when you're trying to find roots of functions, you choose starting x values that the roots are like nice values. So like if, for instance, if you were to like say, let me give an example here. Suppose that, just as an aside here, suppose that you wanted to find the fifth root of 20 using Newton's method. Okay? And this is not part of the problem here, but it's probably a good discussion. Fifth root of 20. Okay? Got to pick an x1. What would a good value for x1 be? Fifth root of 20. Well, 1, okay, okay, so hold on. Let me just write 20 a little better here. I like to be very neat, you know. So Nicholas says that x1 equals 1. Okay. Okay, you could do that. You could do that. The fifth root of 1 equals 1. But the thing is, 1, we're trying to find the fifth root of 20. We're trying to find the fifth root of 20 here. And we're starting with x1 equals 1. The fifth root of 1 is kind of far away from 20. Is there another x value that's closer to 20 that has a nice fifth root? Because see, the closer we are to 20, maybe the less iterations we need. What might be 32, right. 32, the fifth root, very good, Nicholas, the fifth root of 32 is equal to 2. Joe, for 4, and I appreciate all input, the fifth root of 4, offhand, I don't know what that is. I want something I can compute. But the fifth root of 1 or the fifth root of 32, I know what that is. But the fifth root of 32 is a better value to start with. Okay, because 32 is closer to 20 than is 1. All right. So, you know, in our case, 1 is, you know, the sixth root of 1 is not too far away from the sixth root of 2. So, you know, we go with that. Okay, so we get x2 equals 7.6, which incidentally is 1.6 repeating. But what I'm doing is I'm rounding at the 8th decimal place here. Okay. Now, do you think x of 2 equaling 1.66666667. Do you think that's a good approximation to the sixth root of 2? Do you think that's a good approximation? Probably not. And incidentally, too, yeah, and also we want to have our approximation to be correct to 8 decimal places. So we at least need to take another approximation to see if we're correct to 8 decimal places. You know, if the next approximation were also 1.6666667, if x sub 3 were equal to that, then hey, we'd be happy. So okay, I'm using Newton's method. I used it once to get the second approximation. Let's use it again to get the third approximation. But I'm going to use the fraction 7/6. Okay, I'm going to use that fraction because WebAssign's pretty picky about things, about answers, and I don't want to put an approximation ahead of time, so to speak. So, all right, x sub 3, here it is, x sub 3 equals x sub 2 minus the quotient f of x2 divided by f prime of x2. Okay, and then I put in the x2 for my function and derivative, and now I put in the 7/6 power. So I'm just like Newton here, you know. I'm putting in my fraction 7/6, and then I'm actually going to compute this. I'm going to compute it. So 7/6 to the 6th power is equal to this fraction here. And then I want a common denominator. 2 is like 2 over 1. So that's the same as 93,312 over 46,656. And, you know, I do computation. So let me give you a moment to copy this down, and we'll see if there are any questions. Okay, so now I'll be honest here. I was doing everything by hand up to here, but then I actually did use my calculator to get this answer. But keep in mind, Newton would not be able to do that. He or any mathematicians back then would have to compute that out by hand. They might use an abacus. They had some computing tools, but you know what I mean. It would be a chore. But if you need to find your root, you need to find your root, right? Well, Ian, a lot of times back then, the people that studied and went to college were wealthy. They came from wealthy families. I mean, the majority of people didn't go to college back in the 1700s, 1700s. They didn't have community colleges, to my knowledge. And so the mathematicians, yeah, they would spend a lot of time doing computations. But math has evolved and computers have evolved for that very reason, because it takes a lot of time. So, okay, are there any questions up to here before I move to the next page? All right, so well, we have our x3. We have that approximation, and we have the x2. So our first approximation was x1 equals 1. We just chose that. Second approximation was x2. Third approximation is x3. Now at this stage, may I go to the next page? Are we good? Okay. Well, at this stage, here's what we have. Okay, here's x sub 2, the second approximation, and here's the third approximation using Newton's method. Okay, we have not estimated the sixth root of 2 correct to 8 decimal places yet. We don't even have 1 decimal place correct yet, because after the decimal point, x sub 2, you have a 6 there, and for x sub 3, the third approximation after the decimal point, you have a 1. We're not even correct to 1 decimal place yet. And the computations are going to get tedious, right? They're going to get tedious. So what we're going to do is we're going to use Newton's method in Desmos. Okay, we saw Desmos before. We used that before when, let me see, hold on. I know we used it in this class before. I'm trying to recall. Does anybody offhand recall when we used Desmos? No, that's in another class. I'm sorry. Well, how many have heard of Desmos? D-E-S-M-O-S. How many have heard of this? Okay, all right. Joe likes it, and all you need to do, what we're going to do is we're going to get the remaining, well, we're going to get x sub 4, the fourth approximation, fifth approximation, and sixth approximation using Newton's method with Desmos. Now you can use your TI-8384 calculator as well. If you just go to like Google and type in using Newton's method for TI-8384 calculator, there is a way to do that. It involves storing an x value and writing a formula on your calculator, and that's okay. You can learn how to do that. But I think Desmos is actually a little easier, because there's even a picture that goes with it, a geometrical picture. So what I want to do is I want to type Newton's method. Like if you type Newton's method in Desmos in Google, you're going to get the link that I'm going to show you. So you're welcome to do that on your computers. But let me give you a moment just to get, so we're going to get these estimates. All right, let me give you a moment to copy the notes down to here, okay? And then I'll go to Desmos and show you how that works. All right, may I bring up the Desmos here? Let me just, okay, one moment. So in Google, I'm typing Newton's method in Desmos. And it comes up like the very first link. So let me go in there and show you how to use this, because you are going to be using it. Now, for your next exam, I may ask you to show several iterations for a problem, but like I did here for this example. But then the remaining iterations, if you needed to do more to get the accuracy you want, I would let you use Desmos. Okay, so okay, there's the Desmos, and you can see at the bottom or at the top left corner, it says Newton's method. So okay, given information, all right, so blah, all right. I want to change my function here. Okay, so I'm going to click on this. Well, see, I click on it, it shows the graph, but I'm going to change my function into x to the, x to the 6th power minus 2. Okay, there's that function. Okay, and find its derivative. Okay, so all right, it's gonna, Desmos will get the derivative. So initial guess, I need an initial guess. What was my initial guess, class? By they have like a default example on there. 1, okay, good. So I'm gonna change this. I'm gonna just type here a 1. Okay, and now I can look at the iterations. See here how 1's highlighted. I can look at the iterations. So I'm going to click on first iteration. See that? See that? It drew a tangent line to the curve when x equals 1, and it let me see here. Right, and then it crosses the x-axis, and now we're going to use the next value of x2, or we're going to use the value of x2, which incidentally was 7/6. Okay, and then it'll draw a second tangent line. See that? And then we continue the process. third iteration, fourth iteration. See how it's drawing the tangent lines for Newton's method? You're successively then getting your x values. And let's see, fourth iteration, x sub 4 is 1.12246205. X sub 5 is 1.12246,048. Do we have agreement to 8 decimal places? Iteration means just x sub n plus 1 equals x sub n minus the quotient of the function of x sub n divided by the derivative of the function of x sub n. That's what an iteration is of Newton's method. But what's happening is every time you apply Newton's method, well, the Newton's method, you get a value of x. Okay, you get a value of x, and then you draw a tangent line to the curve corresponding to that value of x, and that tangent line will cross the x-axis at a new x value, and then that x value you're going to draw a tangent line to the curve for that new x value. Okay, and you know, obviously it'll be a point on the curve, but the point, the x coordinate, will be that new x value, and then you just keep successively doing it. Okay, does that make sense? Well, John, you're okay with that? Okay, good. Now, Joe's asked, very good. How do we know which iteration is best? How do we know which iteration is best? Well, what we're going to do is we're going to stop. We're not going to put our answer in WebAssign until we know that we have the answer. And you see here the x4 and x5. Okay, so we want to be correct to 8 decimal places. Does the fourth x sub 4 approximation, does the fourth x sub 4, x sub 5, do the fourth and fifth approximations agree to 8 decimal places? So you can see in the screen here x sub 4 and x sub 5. A lot of digits agree after the decimal point, but are there 8 digits of agreement? How many digits of agreement do you see between x sub 4 and x sub 5, between the fourth and fifth iterations? 7, that's right, Ian. You see 7. Now, you want 8, right? You want 8. Okay, so we need another iteration. We need at least one. I think if we had one more iteration, well, no, well, I want to be a little bit careful here. Hold on. Got to be a little bit careful. One moment. One moment here. Actually, if we round, I mean, I want to be a little careful how I say this. What we're going to do is we're going to round the x sub 4 and x sub 5 in the 8th decimal place. And if we do, we see that x sub 5, if we stop at the 8th decimal place, then obviously we're going to round that last decimal place. So x sub 5 rounded to the 8th decimal place would be 1.12246,205. That's what it would be. So that's going to be that's going to be your answer. So, but what you can always do, see, you can take like this, if you needed to do more iterations, right? If you needed to do more iterations, you could take the x sub 5. You can round, you can, Joe, because you're stopping at the 8th decimal place. But let's just say, one moment. One moment. What I'm doing is I'm copying down the x sub 5 number. Okay. And I'm going to do more iterations, but it looks like Desmos only is doing 5 iterations. So if I wanted to do more iterations, what I could do is go back to my initial guess and put in x sub 5 right there. See that? I'm putting in x sub 5. I want to continue the iterations. So I'm gonna update my initial value with the fifth iteration number of x sub 5, the 5th approximation to the root. 1.12246204831. Okay. And then I can say, okay, give me the first iteration, but the first iteration would actually be x sub 6. 6th iteration. Sixth iteration being that we started initially at x sub 1 equals 1. And look what happens. Look what happens. Look at x sub 1. Does x sub 1 agree with x sub 0? It does, right? It does. That means you can stop there. You can stop there. So you want your iterations to agree. And when they agree, you're ready for your answer. So if we want an approximation correct to 8 decimal places, and I understand what you're saying. Let me just see one thing here. Want to be a little bit careful. What they have in example 2 in the book is the answer they have is 1.122462005. Okay, we have 1.122462004 to 8 decimal places, but we're gonna, since we're stopping at 8 decimal places and we want to have the kind of the best answer possible, we're going to round that last decimal place so that we get 1.122462005. I mean, think about it. If you were to give an answer, the best answer you could give to 8 decimal places, you wouldn't give for the root, for the 6th root of 2, you wouldn't give you would not give 1.122462004. You would give 1.122462005, right? Right? That's what you would do, right? And so that's your answer. Okay, are there any questions on this? Any questions at all? Before I go back to the example. Okay, how many of you how many of you is this the first time you've seen Desmos? DESMOS. How many is this the first time maybe? Okay, well, all right. First time in a while, so he says. Okay, all right, well, all right, there we go. Joe, it's your first time. Okay, well, great, great. So it's very nice, very nice. And sure, Nicholas, it can be a nice thing to verify homework, absolutely. And all right, so let me now bring that example back. The Holy Grail. Kelvin calls it the Holy Grail. Well, now Dr. Duty got through Calculus 1 without Desmos a number of years ago, so you can do it too, but it's nice to have. It is nice to have. I love the graphical part too. You could see actually the convergence of those tangent lines too in when you keep doing your successive iterations, which is geometrically very nice. Okay, so therefore the sixth root of 2 is going to be approximately equal to 1.1224620 to 8 decimal places. It's an approximation, right? So we use approximately here. And if you were to do on your calculator, if you were to type in 2 to the 1/6 power, okay, you would see the calculator pretty much as an agreement with this answer. Okay, it agrees with the answer, but you want to get used to using Newton's method, because certainly for your fourth exam, these kind of problems, I'm going to want to see all the iterations with Newton's method. Okay, and I probably will ask you to show work at least on the first couple. So you don't want to just you don't want to just use your calculator and get an answer, right? You want to go through and practice the Newton's method, okay? Because that's what you're learning here. Okay, very good, very good. So, all right. I want to I'll point out another example in the textbook. Are we good with this example? Are there any questions? No questions at all? All right, well then, let me go ahead here and okay, let me go ahead and bring up the ebook again. Let me see, Joe says, so the test, we need to show all of the work. Joe, so what I would say is on the test, I would ask you to show work for maybe the first 2 iterations, like I did here in the example. And then the rest of the iterations you could use Desmos to do, but I would want to see what Desmos is giving you. So like for instance, in this problem, we stopped after 6 iterations because we knew we had the required accuracy we wanted. The estimates for x5 and x6 agreed to 8 decimal places. Okay, so I would want to see, like, let's say you stopped at x6. I would want to see x1, I would want to see, x1 you would choose, x2, x3, maybe, have you show the work on those, iterate those out by hand, like I did in this example. And then x4, x5, x6, you would do, just give me the iterations that Desmos is giving you. Okay, all right, very good, very good. Okay, so let me see here, back to, let me see, where is, one moment, I got to, okay, there it is. Okay, it's very, very interesting section. Okay, so example 3, find correct to 6 decimal places the root of the equation cosine of x equals x. Okay, well, what you're going to do for this is you're going to write the cosine of x equals x as cosine of x minus x equals 0. Because then you're finding the roots of that equation, and that would correspond to the zeros of the polynomial f of x equals cosine of x minus x. But we often say roots of the polynomial too. Okay, and so this is, I'm trying to show you a variety of examples, and you would work this out. Now this here, again, the starting point. How do we pick a starting point? We know how to probably get the function, not too hard to get the function. Okay, pretty easy, right? Newton's method, we just apply it, but the starting point. So they say, in order to guess a suitable value for x1, they sketch the graphs of the cosine and y equals x. They sketch it in figure 6. It appears they intersect at a point whose x-coordinate is somewhat less than 1. So let's take x1 equal to 1. So remember, what you're doing is you're solving, well, you're finding the roots of cosine of x minus x equals 0. But that would be where the cosine of x equals x. So if you look at the figure, they draw the cosine of x function and they draw y equals x. They draw that function. And the two functions intersect. You can see the intersection there. We don't know the coordinate, but we know the x-coordinate is pretty close to x equals 1. So therefore, they pick x equals 1 as the starting point. You see, if you don't pick a good starting point, it could take many, many, many iterations. Okay, and so you want to try to be careful to use the right starting point. And x4 and x5 agree to 6 decimal places. Okay. And therefore, you know to stop there. They make another comment too. Well, are there any questions? Any questions at all on what your they're saying the root of the equation is 0.739085. Are there any questions on that? All right, they make another comment here that instead of using the sketch in figure 6 to get a starting approximation for Newton's method, you could use a more accurate graph. So, like for instance, if you were to like zoom in on where the intersection is between the cosine of x, y equals the cosine of x, and y equals x, you'd see that maybe x1 equals 0.75 it's closer to, it's for the intersection point, that the x-coordinate is closer to 0.75. So if you use that, then you only need to do 3 iterations using Newton's method until you get the accuracy that you need. So you were able to get the estimate of the root, which is 0.739085513, but it took you 1 fewer steps. And this is valuable to think about, because if you're using a computer to approximate a root, you're used to computers working pretty fast, but you could have a very complicated function where it takes a lot of time to get the root. Okay, so it's really a fascinating problem. But are there any questions on that? Okay, then I will stop the recording.